Okay, good morning, everybody. So at the end of the last class, we were talking about inheritance, and we were implementing the constructor for the subclass. Now remember what a constructor is supposed to do. A constructor for any class, whether it's a subclass or not, is supposed to initialize the value of the fields of the object. Right? So the problem that you have in inheritance is that there are fields in the superclass that may need initializing. And so the question is how does the subclass object initialize those superclass fields? Right? Well, if the subclass has access to the fields, then it can just write this dot blah and change the field. Right? So in our counter class, we have access, or we've changed the counter class so that subclasses have access to the field. Right? We've marked the field protected instead of private, which means subclasses can view and modify the field directly. So in our stopping counter constructor, we can write this value equals 0 if we wanted to. But there's a better way to do this. Right? So a subclass can call the superclass constructor to initialize the superclass part of the object. Right? Now this has the advantage that this works even if the superclass field is private. So if your superclass has a private field, that field still needs to be initialized. Right? The way that it gets initialized is by the subclass calling the superclass constructor. Right? The syntax that you use is as follows. Right? So you use the keyword super, right, followed by round brackets. Right? And this calls the superclass no argument constructor. Right? So instead of writing counter round bracket, we write super round bracket, and that calls the counter class no argument constructor, which sets the value to 0. If you want to call a different constructor, right, you just pass in the parameters to that other constructor inside the round brackets. Right. Now, this is where we stopped at the end of last class. So it's not just useful to do this. It turns out you have to do this in Java. Right? So there's a bunch of rules regarding constructors of subclasses. Right? Rule number 1, the first line in the body of every constructor must be a call to another constructor. Now that looks weird, right? Because I just told you a second ago that the other way to write this is as follows. Right? So you can legally write public stopping counter. Right, so there's our no argument stopping counter constructor. You can legally write just this value equals 0. Right, and that would actually work. It would compile. It would do exactly what you wanted to do. But now I'm telling you, hey, the first line of your constructor, which is that one, right, should really be, or must in fact, be a call to another constructor. And we're not calling another constructor there. So if you don't call another constructor on the first line of every one of your constructors that you write, the compiler silently inserts a call to the superclass default or no argument constructor. Right? And so every time we've created a class like point2 or any of your assignments, right, whenever you've written your constructors, you've never called the object constructor. Right? Even though your classes inherit from the object class. Right? The reason you don't do that is because Java inserts the call to the object constructor for you. Right? So in other words, in any one of your classes, so say last assignment you did big binary, right? So in your constructor, if you had a no argument one, I don't think you did, but if you had one, right? What ends up happening is Java silently inserts, right? The compiler silently inserts that for you, right? And that happens in every one of your classes that you've written so far, right? In every one of your constructors, the compiler is actually calling the object, so that's calling the object constructor, the object no argument constructor for you. Right? So if you don't do that, Java does that, which means that constructor there is in reality this constructor here. Right? So that happens whether or not you write it. Now, if your superclass does not have a no-argument constructor, or if the superclass no-argument constructor is private, right, that means it's not accessible to the subclass, so that's an error. Right? So that actually won't compile. So you have to keep that in mind as well. Okay, now, if you're going to call another constructor, then the only place you can call it is from the first line of the constructor. Right? So rule number one, you have to call the constructor. You have to call a constructor. Rule number two, the only place you can do it is from the first line of your constructor. Right? Finally, rule number three, at some point, a superclass constructor has to be called during the construction of an object. Right? And so you can call any superclass constructor. It doesn't have to be the no-argument constructor. Right? You have to call a constructor of the superclass. Right? So at some point, you have to do this. Right? Now, why is rule number three here? Rule number three is here because of constructor chaining. Right? So I'll show you an example of that shortly. All right, so let's look at a second constructor in the stopping counter class. So there's a second constructor that lets us set the value of the counter. Right? So here's our constructor that lets us initialize the value. Right? So what goes here? Well, again, you can write this value equals value if you wanted to. Right? But you could also, oh wait, did I tell you what it is? I didn't. Okay, so let's do it this way. Okay, so what goes here? Well, option number one, you can write this value equals value. Right, so that's fine. Right, why is that fine? Because the field value is accessible to the subclass, so I can just set its value. Right, I don't have to call the superclass no-argument constructor myself because the compiler is going to do it for us. Right? The alternative is to directly call the superclass constructor that sets the value. Right? So this version of the constructor has the advantage that the superclass version of the constructor validates the incoming value. Right? So in other words, I don't have to do it myself. Right? So if I revert it back to the previous, this value equals value, right? Strictly speaking, this is well, it's not incorrect, it's incomplete, right? Because strictly speaking, what we need to do is to make sure that the value is greater than or equal to 0. Right? So the value is less than 0, throw new illegal argument exception. Right? So if you're going to set the field yourself, that's what you have to do. The superclass constructor already does the validation for us, so it's easier just to write super and then value. Right? So instead of writing that, which is legal, by the way, so it's perfectly fine to write this. It's just a better form to instead call the superclass constructor directly. Right? And let the superclass constructor do whatever it is it needs to do. Right? So that's what you could write. Now, there's no reason that you can't use constructor chaining in the subclass. Right? So instead of calling the superclass constructor every time, you're still allowed to call another constructor in the subclass. Right? Again, it has to happen on the first line of the constructor. Right? So in other words, you can still use constructor chaining. Eventually, though, that chain of constructor calls has to lead back to a call to the superclass constructor. So for example, right, to implement the two stopping counter constructors, I can use constructor chaining to chain to the second constructor. Right? So now I'm using this and then 0 to call that constructor down here. Right? This constructor calls the superclass constructor, which satisfies rule number 3. Right? At some point, you have to call the superclass constructor. Right? So that's the other way to write the constructors for this class, right? So set the fields directly, doing all the validation that you have to do, which causes you to repeat code, right? Call the superclass constructors explicitly yourself, right? Or use constructor chaining, and at some point make sure to call the superclass constructor, right? Or any combination of those, as long as you cause a call to the superclass constructor to happen. Right? So you've got lots of choices in implementing your constructors. All right, now, where are we here? Are we still in? Okay, I'm going to switch to the next deck of slides because they overlap anyway. So this is actually inheritance part 2. These slides are on the website, on OnQ, sorry. They're also repeated for a few slides still in part 1. Oh, sorry. Okay, so what's in a subclass? Right, now there's a reason that these rules for constructors exist, right? So there's a reason why you have to call the constructor on the first line of every constructor, right? And similarly, there is a reason why you must call the superclass constructor at some point, right? And so that's because of the way that Java implements inheritance, right? So what exactly is a subclass, right? So a subclass looks like a new class, right? It's just that it has the same contract, right? It has the same methods, same contracts for those methods as its superclass, right? Furthermore, the subclass can add its own additional methods and fields if it wants to, right? But inheritance actually does more than just copy the API of the superclass, right? So it does more than just copy the methods and fields of the superclass, right? A subclass object actually contains a sub-object of the type of the parent class. Right? So in other words, every stopping counter has a counter inside of it. Right? The subclass, the superclass sub-object has to be constructed. Right? So if every stopping counter has a counter inside of it, that counterpart of the stopping counter needs to be initialized by a constructor. Right? Just like you would initialize any other object. Right? And so the mechanism that Java uses to perform the construction of the superclass sub-object is to force the programmer to call the superclass constructor at some point. Right? So in other words, to initialize the stopping counterpart, to initialize the counterpart of a stopping counter, you have to call a counter constructor at some point. Right? So why do you need to do it? Because a stopping counter is a counter. Right? So remember, that's what inheritance means. Right? And the counterpart of the stopping counter needs to be constructed. What is this picture? Okay, so this is a picture of what actually happens. Right, so this is an incorrect picture of what actually happens. Sorry. Stopping counter. Oh, sorry. Let me break that line. All right, so when you write that line of code, we're making a new stopping counter object whose starting value is 1. Right? So what happens is, when you call new, right, you get a stopping counter object that appears somewhere in memory. Okay, so new calls the stopping counter constructor, passing in the value 1. Right? So the stopping counter constructor starts to run. Right? So what does the stopping counter constructor do? Right? So on the first line of that constructor, it calls the superclass constructor. Right? So it initializes. So what happens is the counter object gets created. Right? And now this counter object needs to get initialized. What does that mean? The counter constructor has to start running. Right? What does the counter constructor end up doing? Well, it has to initialize, or it causes the object part of the counter to get initialized. Right? Remember that big O object, that's the superclass of every class in Java. Right? So in this case, it's the direct superclass of counter. Right? So now the object part of your counter gets created, and its constructor has to run. Right? I don't know what that constructor does, right? But it does something. I haven't looked at the source code for object. I don't know what's in it. Right? If it has fields, it has to set those fields. Other than that, I have no idea what's going on in that constructor. Right? But it runs and initializes that object. Right? When it's done, right, the object part of our stopping counter is now initialized. Right? And that means that the counter constructor can finish running. Right? So remember, the counter constructor on its first line, it's calling the object constructor. Right? When the object constructor finishes running, the counter constructor can finish running. What does it do? It sets the value. Right? So value gets set to 1. Right? Now the counter constructor is finished running, so the stopping counter constructor can now finish running. Right? Stopping counter only has one line. Right? So let me just change what's on the board. Right? So the way that we've implemented the stopping counter constructor is as follows. Right, so here we've written super value, sorry. Right, and then there's nothing after it. So the stopping counter constructor finishes running, right? And you've now got a completely initialized stopping counter object, right? So one more time, very quickly, right? Make a stopping counter object, its constructor starts to run, right? That causes the counter object, the counter part of the stopping counter to be initialized. Its constructor runs. That causes the object part of our stopping counter to be initialized, right? And it finishes running, right? So the object constructor runs and finishes running, right? So notice the order in which the objects are actually completed, right? The innermost object, big O object, is the first object that's actually completely constructed, right? Only when the object part of the stopping counter is constructed can the counter part of the stopping counter be constructed, right? So object gets built first, counter gets built second, and finally the stopping counter part, which is the constructor that we called in the first place, right? Only then can it finish running, right? So the parts of the stopping counter are built from the inside out. Right? Object finishes being built first, then counter, then stopping counter. Right? And that's the reason why you have to call a constructor on the first line of every constructor. Right? Stopping counter has to call the counter constructor so that it can initialize the counter part. The counter constructor has to call the object constructor so that it can initialize the object part. Right? Okay. Finally, right, after talking about the constructors, we can finally finish our implementation of stopping counter. Right, so the last part of stopping counter is to override advance. Right, so when we override advance, we want to stop counting when we hit integer max value. Right, but that's easy to do. Right, update your Java doc to indicate that this advance method does something different. Right, so if the value of the counter is not equal to integer max value, just increment the counter by 1. Otherwise, do nothing, right? And that's it. So it's dead easy to override advance in this case, right? But you've now got a stopping counter that actually stops counting when you hit integer max value, right? Instead of wrapping around to 0. All right, so you can do the same. You can do something very similar. Instead of stopping the counter, you can throw an exception, right? Turns out this is not a good idea, but you can do it. Right? So I'm going to make another class called throwing counter that also uses inheritance to extend the counter class. Right? Again, no fields. Right? I don't need a field to store the value because the counter class already has one. Right? How do I implement the constructors? Well, it's easy. Right? Call the superclass constructor on the first line. Right? So we initialize, we call the superclass constructor passing in 0 in this case. Right? Here we call the superclass constructor passing in value. No problem. Right? Override advance. This one throws an exception if it hits integer max value, so no problem, right? If the value is not integer max value, add 1 to the value, otherwise throw an exception. And that's it, you're done. Right? So inheritance, in many cases, makes it very easy to reuse the implementation of an existing class. Right? You can override methods that you inherit from the superclass to change the way that those methods behave. Right? Implementing the constructors is usually pretty straightforward. Right? Call the superclass constructor and then initialize whatever other fields you need to. Right? Okay, now, should you use inheritance in this example? Maybe, maybe not, right? It's a very simple example, right? But there are alternatives, right? So you should always keep in mind that there's almost always a different way to do things in programming, which is part of what makes programming hard, right? Choosing between the alternatives is not easy, right? Okay, so we used inheritance to change the way that the advanced method worked, right? So in other words, we used it to change the behavior of our counter. But that's the only thing. The only difference in the counters is that something different happens when you hit the maximum value, right? So using inheritance, we made separate classes that override the advanced method, right? There's another approach. So the alternative approach is to encapsulate the behavior of what happens when the counter is advanced past its maximum value in an object, right? So in other words, right, you can take what we did in advance, right, that governed how we changed the value when it hit integer max value, and you can put that into an object, right? And then you can make that object a field of the counter class. Right? So I'm not going to show you or go into the implementation of that particular type of counter. Right? I'm just pointing out that there is a different way to do this. All right, now what about equals? So we talked about two different ways to implement equals, right? One uses get class. The second alternative uses instance of, right? The choice that you make between using get class and instance of affects whether or not equals works in an inheritance hierarchy, right? So can I compare different kinds of counters for equality, right? So in other words, can I compare a stopping counter to a regular counter to see if they're equal, right? If you don't think about it too hard, you would say, well, yeah, I should be able to compare those two counters, right? If they have the same value, they're equal, right? But suppose we used get class to implement equals, right? And remember, right? So remember what get class means, right? So if you use get class to implement equals, you're saying two objects are equal, can be equal if and only if they have the exact same type, right? So what does that mean, right? So what does equals look like, right? So in counter, if you use get class, it would look as follows, right? Check if this is equal to obj, right? Check if obj is null. Then finally check if this class is not equal to obj get class, right? In other words, if the types of the obj and counter are different, right, then they're not equal, right? Only after that do you do the cast and then compare their values. So if you implement equals in that way, then I can make two counters, right? C1 and C2, they're both counter objects, right? If I write C1 equals C2, I'm going to get true because they're both counter objects and their values are both 0, right? Now, stopping counter inherits equals from counter, right? So without overriding equals, right, in stopping counter, I can make two stopping counter objects and write equals. This will also print true, right? Because they're both stopping counter objects and their values are both 0, right? What you cannot do is to write the following, right? Make two counter objects, one's a counter, one's a stopping counter object, right? Their values are both 0, but if you write C1 equals C2, you get false. Why? Because one's a counter and one's a stopping counter, right? Get class for counter is different than get class for stopping counter. Right? Similarly, if you make two other counters, one's a stopping counter and one's a throwing counter, and ask if they're equal, the answer is always false, even if their values are equal, right? And that may not be how you want your counters to behave, right? It might be how you want your counters to behave, it might not be, right? If you don't want to allow cross-class comparisons for equals, use get class. If you want to allow what are called mixed type comparisons, then you must use instance of, right? So if I want a counter to be equal to a stopping counter or a throwing counter, I have to use instance of when I implement equals in the counter class, right? In the superclass, right? You have to use instance of. Right? So remember what instance of does, right? Instance of does the same thing as getClass, but it does more, right? So if obj, instance of counter, is asking, is obj a counter? Is obj a subclass of counter? Right? Or does obj implement the counter interface, which doesn't make sense in this case because counter is a class, right? So instance of returns true if obj is a subclass object of counter. Right? So in other words, if obj is a stopping counter, obj instance of counter is true. Right? If obj is a throwing counter, then obj instance of counter is true. Right? So now this if statement does not run if you pass in a stopping counter here. Right? And now cast whatever obj is to a counter. Right? You don't have to cast it to stopping counter. You don't have to cast it to throwing counter. You're in the counter class. Right? So cast it to a counter type and then check if their values are equal. Yeah? Oh, yeah. Right. And now this allows cross-type comparisons. Right? So make two counters, check if they're equals. The answer is yes. Right? Make two stopping counters, test if they're equals. The answer is yes. Right? Make a counter and a stopping counter, ask if they're equals, and now the answer is yes, right? Because their values are both 0, and they're both instances of the counter class. Right? In other words, they're both either subclasses of counter or counter objects, or actually counter objects. Right? Similarly, if I make a stopping counter and a throwing counter and ask if they're equal, right, the answer is also true. Right? In this example, we have not overridden equals in stopping counter or throwing counter. Right? We've only implemented equals in the counter class itself. Right? Stopping counter inherits equals from counter. Throwing counter inherits equals from counter. Okay, so that was why I showed you the two different reasons, the two different ways of implementing equals. Right? Use getClass if you want to prevent cross-type comparisons for equals. Use instance of if you want to allow cross-type comparisons for equals. Right? Okay, some of that code was a little funny that I've shown you. Right? So here I wrote counter 3 equals new stopping counter. Right? And I wrote counter 4 equals new throwing counter. Notice that the type on the left-hand side does not match the type on the right-hand side. Right? Well, at least they're not exactly the same. Right? Now, why can I write this? So it all comes back to substitutability. Right? A stopping counter, right, inherits from counter. What does that mean? Stopping counter is a counter. Right? Anywhere I need a counter object, like on the right-hand side of this assignment, I can use a stopping counter object. Right? So stopping counter is substitutable for counter. What does that mean? I can store a stopping counter object reference in a counter variable. Right? The opposite's not true. Right? I cannot store a counter in a stopping counter variable. Right? Again, inheritance is strictly one way. Right? And so this actually asks this leads to the question of how many types does an object actually have? Right? And so with the exception of java.lang object, right, all objects in Java have more than one type. Right? So what are the types of an object? Well, it includes whatever class the object is defined, the object's own class type. Right? So a stopping counter, one of its types is stopping counter. Right? But its other types include all of its ancestor class types. So what does that mean? It means the type of a stopping counter includes counter, and it includes object. Right? Furthermore, the type includes all of the interface types. So if counter implements the comparable interface, then stopping counter also has the type comparable. Right? So here's an example, point 2. Right? Now point 2, we didn't write extends object, but that's what it does because everything extends object. Right? It also implements comparable. Right? So what types does point 2 have? Well, it has the type point 2, it has the type object, and it has the type comparable point 2. Right? That object, so an object of type point 2 actually has 3 different types. Right? Stopping counter extends counter and implements the comparable interface. So what types does it have? Well, stopping counter. Right? Counter, right? Now remember, counter extends object, so object, right? And we implement the comparable counter interface, so it also has the type comparable counter, right? So stopping counter actually has 4 different types in Java, right? Here's string, right? This is the string class from the Java standard library, right? Notice that string is marked final, right? So if you mark a class as being final, that means you cannot inherit from that class, right? So in other words, the inheritance hierarchy stops at string, right? String has no descendant classes, right? There are no subclasses of string. So that's what the word final means when you mark a class as being final, right? So string extends object and it implements these 3 interfaces, right? So what are the types of string? Well, string, object, serializable, comparable, and car sequence, right? So it has 5 types. All right, so the fact that almost every object in Java has more than one type leads to the concept called polymorphism. Right? So the dictionary definition of polymorphism is the condition of occurring in several different forms. Right? So Java has what's called subtype polymorphism. Subtypes are substitutable for their ancestor types, right? So a counter is substitutable for object, stopping counter is substitutable for counter. It's also substitutable for object, right? How does this work in Java? Well, I just told you that all objects have more than one type, right? So polymorphism is made possible in Java because an object has more than one type, right? An object includes all of the types of its ancestor classes, right? So what does that mean? Well, it has a bunch of implications, right? So when I make a variable, right, of type counter, right, that says that C, right, can only store a reference to a counter object, right? But it can also store a reference to anything that's substitutable for a counter object, right? So using C, what can I store? I can store null, right, no object. I can store a reference to a counter, or I can store a reference to an object having a type that's a descendant of counter, right? So in other words, I can store a stopping counter reference inside a counter variable. I can store a throwing counter reference inside of a counter variable. Right? Why does that work? Because a stopping counter is a counter, right? A throwing counter is a counter. Right? The declared type of a variable or a field or a parameter, right, determines what operations can be performed using that variable, field, or parameter. Okay? So if I write set t equals new tree set, right, and then I add the string hello to the set, that's legal, right? Why is that legal? Because all sets, right, all sets have an add method, right? Now, the thing on the right-hand side is a tree set, right? Tree set's an example of what's called a sorted set, and sorted sets have this method called first, which returns the first element of the set, right? Because the set's sorted, right? So, there is the notion of the first element, right? But if you write this, the compiler will flag this as a compile time error, right? Now, why is it flagged that as a compile time error? Because you told the compiler that T is a plain old set, right? So T is a plain old set. So the declared type of T is the thing on the left-hand side, right? So that's set, right? Set doesn't have a first method, right? If you look at the set documentation, there's no method called first. So the compiler looks at this and says, what's T? Well, T is a set. Does set have a first method? The answer is no, so this is a compile time error, right? Even though the object that you stored in T has a first method, right? So the declared type determines what methods can you call using a variable, field, or parameter. Right? Now, if I change the declared type, so if I change it to sorted set, right, and then call first, right, now that works. Why? Because sorted set has a first method, right? So that works. What about the thing on the right-hand side? Right? So what about this thing over here? Right? So the thing on the right-hand side, that's the runtime type. Right? So in an assignment or initialization expression, right, so whenever you use equals, right, the equal operator. The type of the value on the right-hand side is called the runtime type or actual type, right? So when I write C equals new stopping counter, right, the declared type of C is counter. The actual or runtime type of C is stopping counter, right? So now there's two different types at play here, right? So what does the runtime, why does the runtime type matter? Because the runtime type determines which version of a non-static method is called when you use that variable. Right? So think about that for a second. What version of the method is going to get called when you use that variable? Right? So here's obj. Declared type is big O object, right? But its runtime type is counter. So I store a counter object in an object reference, right? If I call toString on obj, which version of toString do I get? Right? Well, I don't get the object version of toString, I get the counter version of toString. The runtime type determines which version of the method you get. Right? So in other words, when I do obj toString, I get the counter version of toString, right? Because it's the runtime type that determines the actual version of the method that gets run. So here's a print method inside the class printer, right? It takes in a parameter of type big O object, right? So using the parameter obj, what methods can I call? Well, I can call any method that's in the class object. Right? So I can call toString, for example. Right? The runtime type of obj determines which version of toString that is called. Right? So if I print the string s, right, I get the string version of toString. If I print the list t, I get the array list version of toString. And if I print the date o, I get the date version of toString. Right? Even though o, its declared type is big O object. Right? It's the runtime type that matters. Right? So when I pass O to my print method, right, what happens at runtime is that it's the date version of toString that gets called. Right? So declared type allows the compiler to check which versions of the method can be legally called. Right? So the declared type affects compilation. The runtime or actual type determines what happens when your program actually runs. All right. So observe that the compiler has no idea which version of toString gets called in the print method. Right? So in the print method, this is all that the compiler gets to see. Right? The compiler can see that I'm calling the toString method belonging to obj. Right? And as far as the compiler is concerned, that's a big O object. Right? That's all the compiler sees. Furthermore, if you try to compile this class here, it compiles without any issues. Right? So type in those 3 lines of code, compile it, and the Java compiler will be perfectly happy with that code. Right? The actual version of toString that gets called by that method can't be determined until runtime. Right? So it's not until you actually write a complete program and run the program that something figures out which version of toString that's called. Right? It turns out the something that figures it out is the Java virtual machine. Right? So the runtime, using the runtime type to determine which version of a method to call is this thing called dynamic dispatch. Right? It also has the name late binding. Right? So it's dynamic because it happens at runtime. Right? Dispatch means which version of the method to call. Right? So that's why it's given the name dynamic dispatch. Late binding means the same thing. So the word late means it does not happen at compile time. It happens at runtime. Binding means which version of the method gets called. Right? So these are both they're both equivalent terms for the same mechanism. Right? Okay, so that print example is a simple example of the power of polymorphism. Right? The fact that an object has more than one type. Right? So look at this print method, right? So I can write this print method, right? And this works for anything that I pass into this method. right? Which is a very powerful idea, right? You can't do that in C. Well, you can sort of do it in C. I don't know if they taught you how to do it in C, right? But in C, you normally got something like int and then something here, right? Or array of char or something like that, right? And then in C, you're stuck passing in an int or an array of char or something else, right? You have to match the types here exactly, right? There is a way around it, but, well, there's sort of a way around it, right? But in Java, right, I can write this one method and pass in anything to it, and it works, right? So the programmer, a programmer, sorry, can write a method using the interface of an ancestor type. So what does that mean? I can look at the contract for a method belonging to big O object, right? I can write the method using only the contract for big O object, right? And I know exactly what the method's going to do, right? Regardless of the type of object that I pass in, right? So consider the methods in the class Java util collections. Oh, sorry. Do I have a link to that? I do. Right, so here, oh wait, this is the wrong, sorry. There's an S missing in that link. There we go. So here's the utility class collections, right? Here's the method addAll. Right? AddAll, its parameter type is big C collection, right? And I can add a list of elements to this collection, right? And I know this works. It doesn't matter what type of collection I pass in, it works, right? So what does that mean? I can pass in a list, and this method will add all the elements to the list, right? I can pass in a set, and this method will add all the elements to the set. I can pass in a tree set, and this method will add all the elements to the tree set, and the elements will be in sorted order, right? So by using the interface name here, right, I can write one method that behaves differently depending on the type of object that's passed in. Right? And so that's a very powerful idea. Right? Here's binary search. It'll binary search any list. Right? I can pass in an array list. I can pass in a linked list. I can make my own list type, pass it in, and it works. Right? It does binary search for me. It doesn't matter what the actual type of list is. It still works. Right? And you can keep on going down the list for any of these methods. Right? All of the methods in the most of the methods in the collections utility class, right, are written in terms of the interfaces, not in terms of the actual classes, right? So if you look in the methods, none of these methods will take in an array list, or a linked list, or a hash set, or a hash map, right? They all take in interface types, right? And that lets you pass in many different kinds of objects to those methods, and the methods just work. Okay, so that's the end of that lecture. I think I'll stop there. There's actually been a lot of concepts that I've thrown at you today. Your assignment 5 is out. It's relatively short. But you don't have that long to do it, right? So you've got I think a week today to submit that assignment. It is shorter than the previous assignments because we're running out of time. All right, any questions? Super, see you next week. Have a good weekend.